Hello, welcome back. In this segment, I wanted to demonstrate how the jump instruction is encoded at the binary level. So, for example, take this assembly code. We have move 1 to ECX, and then we have a jump to label L1. The label L1 starts here, okay? And then the rest of the code continues. Of course, in this process, we are not going to execute this statement because we have a jump. The question now is, how is jump encoded at the binary level? Let's compile this code and see the binary op. Okay, so I'm going to call the assembler to compile this first without doing the linking. Okay, and now we can just look at, for example, object dump minus disassemble. You will see the jump statement is over here. Move 1 to EDX won't be executed because we are jumping to C. C is at this address and it has all the rest of the code. Okay. But interestingly, what is the meaning of C? Okay. This portion is assembly. This portion is assembly code, right? Whatever you're saying with move, jump, this is assembly code. And this is actual machine code. Okay. So what runs is the machine code, of course. And if you look at the jump statement, in the way it is encoded in the machine code is EB05. Okay. Now we need to ask ourselves, what is the meaning of EB05? EB stands for the jump instruction, but 05 is the relative address. Okay. Let's understand that more precisely. So if you consider 05 relative to the next address, okay, what is the next address? The next address is 7, right? If you add 7 with 5, you get 12. Okay, 7 plus 5 is 12. And that's exactly what we are seeing here as part of the jump statement. Okay, so let's continue the same after linking the code with runtime necessary libraries, right? This is going to be after the addresses are resolved, and we will look at the output. And we can see now that we have a number, JMP 8048060. Earlier we had jump C, okay? But if you look at the constant remained the same, okay? That's interesting. The reason is that if you take the next address, what is the next address? The next address is 8048005B, right? If you add 5 to it, so this is hex addition, right? So B means 11. 11 plus 5 is 16. 16 mod 16 is 0. Carry over 1. 5 plus 1 is 6. So the rest are all similar. Okay, so you can find out the actual jump address by taking the next statement address, right? And add to this constant. And that's the reason why you are seeing 8048060 in the assembly code. Okay, this is how the jump addresses are encoded. Okay, to summarize, it uses the program counter. The program counter is going to point to the next instruction to be executed while this is running. So all we are doing is take the program counter value, which will be 8048005B plus 05, and that will give us the exact location to jump.